Thank you, Doug. Our next panelist is Eric Geist. Eric is a research geophysicist at the USGS Pacific Coastal and Marine Science Center. Eric is an expert on tsunamis, and his work includes modeling the formation of tsunamis, as well as devising probabilistic estimates for their occurrence in various regions of the world, including right here in California.
Thanks. Okay, just a little bit about what tsunamis are all about. It's a different kind of wave. Fortunately, we don't have a lot of us don't have direct experience of tsunamis. So a little explanation is in order. We think of tsunamis as occurring in terms of their evolution in three stages: generation, propagation, or how they travel across the ocean, and run-up. So these are illustrated here. To generate a tsunami, you need something that displaces the entire water column. So fortunately, there's very few things that can do that. Very large magnitude earthquakes, as shown here, a large submarine landslides, even asteroid impacts. Once that's displaced, you're moving this huge volume of water up and down above where it wants to sit at ambient sea level. It's going to spread out in all different directions. And here we have a cross-section or a side view of what it might look like. And once it's generated, you generate really two tsunamis. One, the local tsunami propagating to the local shoreline, and a transoceanic or far-field tsunami that's propagating all across the Pacific Ocean. So once they're generated, they're very persistent. They can travel very long distances. And as they evolve as they cross the ocean based on primarily the water depth. And as you go from deep water to shallow water, the tsunami starts to slow. So we saw that 500 miles per hour. As you get into shallower and shallower water, it slows to maybe, when it gets to the beach, maybe 30 to 40 miles per hour. One of our important rules of thumb is if you can see a tsunami, it's probably too late to outrun it. And they are pretty deceptive. If you see some of these videos, you don't really know it's a wave because a lot of the time it's not breaking. So it's slowing as it's coming into shore. The wavelength is decreasing. In order to conserve this massive volume of water, the amplitude has to go up. So this is our amplification part of the propagation problem. And then it undergoes a pretty radical transformation as it hits shore, this process of run-up. Run-up also refers to a vertical measure at the point of farthest inundation. So run-up is a vertical measure. If you see these run-up figures in the newspaper, that's measured relative to the ambient sea level, and inundation is a horizontal measure. So here's an image from NOAA about the far-field distribution of energy from the Japan tsunami. Of course, the tsunami waves are going all throughout the Pacific basin. There was a hospital that was flooded way down in New Guinea. But you can see this very complex pattern of energy as it propagates through the Pacific Ocean. And you can see right here, this is a bathymetric feature called the Hess rise. Some of the energy got split off there, and that sent quite a bit of energy to California, which caused some of the damage to our small harbors. So California has a kind of an interesting history of tsunamis. I kind of abbreviate here. Our San Francisco tide gauge station was one of 3 tide gauge stations put in right after the gold rush in 1949. And just soon, 1849, soon after, there was a pair of earthquakes from Japan, only a couple days apart, that were recorded. They had the person looking at the tide gauge records saying, what are these waves, And they took some detective work, but they figured out it was this earthquake in Japan that sent these tsunami waves over, and they were recorded. So that was our earliest instrumental recording of tsunamis in California. The San Francisco tide gauge record has recorded over 50 tsunamis. So tsunamis can vary in size just like earthquakes. So we talk about micro tsunamis as well as these very large tsunamis. The largest tsunamis we've historically had come from Alaska. The 1946 Aleutians tsunami was very damaging on the outer coast especially. The larger magnitude 9 earthquakes generated tsunamis that did some damage inside San Francisco Bay, the largest being the 1964 Alaska tsunami. The Chilean tsunami was the largest earthquake instrumentally recorded, magnitude 9.5. And then, of course, we have our most recent magnitude 9 earthquake from Japan. So I don't know how many people can see the URL on the bottom, but the California Geological Survey has just recently, in the last couple of years, put out these tsunami inundation maps for evacuation purposes. So these are very worst-case scenarios in terms of evacuation. I show the one for the Berkeley area here. So these would be interesting. You can just Google California Geological Survey tsunami maps and pull up the map that you might be interested in. And finally, to leave you with a big wild card in terms of tsunami risk is submarine landslides. There's some things we do know about submarine landslides in terms of the tsunamis they generate. You can kind of see here the wave is a lot more complex. It's asymmetric as compared to the earthquake-generated tsunami that I showed in the first slides. So we can understand the hydrodynamics, the fluid dynamics of landslide tsunamis a little bit, but we don't have an instrumental record of submarine landslides like we do for earthquakes. We know that they're very rare, but we don't know exactly the probabilities of these events occurring. So there's a lot we don't know about submarine landslides, so I think I'll just leave you with that point. This, by the way, is a simulation of a submarine landslide, some work we did off of Puerto Rico. And you can see the large run-ups, amplitudes here, but they dissipate pretty quickly as you go towards shore.